So as I mentioned at the end of the previous video, we can combine all of those individual gas laws relating pressure and volume, where some things are held constant, some things are not held constant, into one single equation, which is generally what we use to describe gases. And we call this the ideal gas law. And what this equation looks like, again, this is probably familiar to many of you, is PV equals nRT. So we have all of those properties that we were talking about before, P, V, N, and T, and the relationships hold that we showed before. So pressure and temperature, if they go up together. Volume and temperature go up together. N and V go up together, but pressure and volume are inversely related to each other. The thing that gets added here is now we know what the constant is. So this is our proportionality constant, and this is known as the universal gas constant or the ideal gas constant. And we give it the symbol R. I don't know why. But it has different values depending on what units you use for all the different things here. So one of those common units is to use liters times atmospheres over moles times Kelvin. And in those units, the value of R is 0.08206. So that is equal to R. But if you write it in different units, you'll get a different value. So another common one is to write it in terms of joules per mole times Kelvin, in which case R is equal to 8.3145. These are the same, right? All that's changing is we're writing it in different units. So this captures all the same concepts that we have in the individual gas laws relating pressure, volume, number of moles, and temperature into a single law that we can use under ideal conditions. Now, why is this called the ideal gas law? Well, it comes to the idea of an ideal gas. And an ideal gas is one where there are no forces between the gas particles. Meaning that the gas molecules don't push or pull on each other at all. This isn't actually true, but the gases are so far apart from each other on an atomic and molecular scale that you can basically ignore these forces for the most part. At the very end of this chapter, I think we'll briefly talk about when you need to actually worry about them. And we also assume that the gas particles, the molecules or atoms that are present in the gas, take up no volume. Now, of course, they actually do take up some volume, but it's very small compared to how far away they are from each other. So we essentially treat them as little tiny points of mass that don't actually take up any space. And that's what we consider an ideal gas. And under these conditions, all gases behave identically. And we can use one equation to describe every single gas. They all obey this ideal gas law and all use the same universal gas constant, which is really useful. And this, just to be clear, works really well under most conditions. So for things that are gases at room temperature and pressure, if we're talking about, say, our atmosphere and gases in the atmosphere, using the ideal gas law is a very, very good assumption. And your calculations with it will give you very close to what the actual measured values are if you were doing some sort of problem involving the ideal gas law. And when I mean most conditions, this is usually thinking about like about 1 atmosphere of pressure and in the range of 0 to 40 degrees Celsius. Now, of course, this will depend on specifically what kind of thing you're talking about, what kind of gases. But for most gases, under these conditions, the ideal gas law is a really, really good approximation. Okay, one additional thing is that we often think about gases at what we call STP, standard temperature and pressure. This sort of gives us a reference point to compare everything to. And the specific standard temperature and pressure that we choose are 0 degrees Celsius, or 273.15 Kelvin, and 1 atmosphere. Well, technically it's 1 bar, but that's about equal to 1 atmosphere of pressure. As you know, they're not quite the same as I showed in the video on pressure, but for our purposes, we'll consider them to be equal. All right, and one one thing to note about the ideal gas law is that we can calculate what's the volume of 1 mole of an ideal gas at STP. What is the volume? And again, because the ideal gas law applies to all gases, this will hold no matter what gas we're talking about. It could be nitrogen, it could be carbon dioxide, it could be argon, it could be oxygen. All of these will have the same volume for 1 mole of gas. They won't have the same density. They will weigh different amounts because 1 mole just weighs different. That's the idea of a molar mass, which we've used so much in this class. But we can go ahead and calculate this. So we know standard temperature and pressure, so we can say, so we're going to use PV equals nRT. We know N is equal to 1 mole. By definition, we're asking the question, how much does 1 mole take up? We know that T is 273 Kelvin. I'm going to leave off the 0.15 for now. And we know that the pressure is equal to 1 atmosphere. Again, we could use bar to be a little bit more specific. So we can go ahead and solve this. We can say V is equal to nRT divided by P. So I'm just dividing by P on both sides here. Just to rearrange this equation first. And now we'll go ahead and plug in all the values that we need. All right, so we have 1 mole here. R, again, from above, if you go back in the videos, you can see this, 0.08206 liters times atmospheres over moles times Kelvin. And I'm picking this particular value of R with these units because we're going to express, we want the volume in liters, and we going to express our pressure in atmospheres. So that leads to everything canceling out, except for liters, which we want. Temperature, 273 Kelvin. Again, always when dealing with gases, you always have to use Kelvin, not degrees Celsius. And then divide by our pressure, which is 1 atmosphere. If we plug all this in, again, our units should all cancel except for liters. We get 22.4 liters. And this is what we call the molar volume, or the volume of 1 mole of gas for an ideal gas at standard temperature and pressure. That's a useful value to sort of have in the back of your mind. You don't worry about memorizing it, but give you approximate. It's 22 liters. It's a decent size for 1 mole of gas. Whereas 1 mole of, say, water is only 18 milliliters, right? And so you can see the very big difference in densities between gases versus liquids and solids. All right, and so this concludes our sort of explanation of the ideal gas law. We'll have one more video where we just work through a couple more a calculation or two involving gases, just to give you some idea of things to pay attention to and an example of how to do that.